Dark matter is one of the quietest mysteries in the universe. It does not shine, it does not glow, and it does not announce itself through any ordinary form of light. We cannot simply point a telescope toward a region of space and see dark matter itself. And yet, everywhere we look on the largest scales, the universe seems to be shaped by something that we cannot directly see. Galaxies rotate as though they contain far more mass than the stars and gas we can observe. Galaxy clusters hold together under the influence of gravity that appears stronger than visible matter alone can provide. Light from distant galaxies bends as it travels through regions containing invisible mass. Across billions of years, the large-scale structure of the cosmos has grown in patterns that strongly suggest the presence of an unseen component. We call it dark matter, not because we know exactly what it is, but because we know that something is there. Tonight, there is no need to solve this mystery. There is no experiment you need to complete, and no equation you need to understand. You can simply let your attention drift into the darkness between the stars, where the visible universe becomes only a small part of a much larger story, and where the unseen may quietly shape almost everything we see. Imagine looking up at the night sky on a clear evening. The stars seem to form a scattered field of points, some bright and some faint, some close by and others unimaginably distant. The Milky Way may appear as a pale band stretching across the darkness, and beyond it are galaxies so far away that their light has traveled for millions or billions of years before reaching Earth. Everything you can see with your eyes is made from ordinary matter, the familiar material that forms stars, planets, dust, gas, rocks, oceans, and living things. But this visible material represents only a small portion of the matter and energy that make up the universe. Most of the matter appears to be dark matter, and most of the total cosmic energy budget is associated with dark energy, a separate mystery connected with the accelerated expansion of space. Dark matter and dark energy are not the same thing. Dark matter behaves gravitationally like matter, helping structures form and remain bound, while dark energy is associated with the large-scale acceleration of cosmic expansion. Tonight, our attention stays with the quieter mystery, the invisible mass whose presence is written into the motion and structure of the universe. The story of dark matter begins with a simple idea that is almost impossible to notice in ordinary life. Gravity tells matter how to move, and the motion of matter tells us something about how much mass is present. If you watch a planet orbit a star, you can learn about the star's mass from the planet's motion. If you observe stars orbiting within a galaxy, their speeds can reveal how much mass surrounds them. If you measure galaxies moving inside a cluster, their motions reveal the gravitational strength of the entire cluster. This is one of the great tools of astronomy. We do not need to see every piece of matter directly. We can infer the presence of mass from what gravity does. A planet can betray the existence of an unseen moon. A star can reveal the presence of an invisible companion. A galaxy can reveal a much larger invisible structure surrounding it. In the early 20th century, astronomers studying galaxies and galaxy clusters began finding clues that the visible matter was not enough to explain what they observed. One of the most famous examples involved galaxy clusters, enormous collections of galaxies held together by gravity. When astronomers measured how quickly galaxies moved within a cluster, they found that the motions could not easily be explained by the visible stars and gas alone. If the clusters contained only the matter we could see, many of them should not have remained gravitationally bound for as long as they apparently had. Something unseen seemed to be providing additional gravity. These early observations did not immediately produce a complete theory of dark matter, but they established an important possibility. Perhaps the universe contained a large amount of matter that did not shine. Another crucial clue emerged from the rotation of spiral galaxies. A spiral galaxy, such as the Milky Way, is a vast system of stars, gas, dust, and other material rotating around its center. If most of the mass were concentrated where most of the visible light is found, we would expect the orbital speeds of stars to change with distance from the center in a particular way. Instead, observations revealed something surprising. Stars far from the galactic center can orbit at speeds that remain remarkably high, rather than slowing down as much as a simple visible matter model would suggest. The outer regions of galaxies appear to be moving as though they are embedded in a much larger gravitational structure. This unseen structure is often described as a dark matter halo, extending far beyond the luminous disk of the galaxy. Picture the Milky Way not simply as the glowing spiral band we see in artistic illustrations, but as a luminous island surrounded by an enormous, invisible cloud of mass. The stars and gas occupy only the bright inner region. Around them stretches a much larger halo, difficult to observe directly, whose gravitational influence reaches far beyond the visible disk. The Sun orbits within this larger system. The planets orbit the Sun orbits within the galaxy, and the galaxy itself moves within the larger gravitational environment of the local group. At every level, motion provides clues about the mass that shapes it. The universe is therefore not only what shines, it is also what moves because something is pulling on it. This idea can feel strange because human vision is so strongly connected to our understanding of the world. When we enter a dark room, we usually assume that the room is empty until we can see what is inside. Astronomy teaches us a different lesson. Space can contain something that does not emit visible light, and yet has a powerful gravitational influence. Dark matter does not need to shine for gravity to reveal it. It can remain invisible while galaxies orbit within its influence, clusters move through it, and light bends around concentrations of it. In this sense, dark matter is not truly hidden. It is indirect. We do not see the thing itself, but we see its effects. One of the most beautiful examples comes from gravitational lensing. According to general relativity, gravity changes the geometry of space-time, and light follows paths through that curved geometry. A massive object between us and a distant galaxy can therefore bend and distort the light coming from behind it. Galaxy clusters can act like enormous cosmic lenses, magnifying and stretching the images of more distant galaxies. By carefully studying these distortions, astronomers can reconstruct how mass is distributed through the cluster. When they compare the inferred mass with the visible stars and gas, they find that much of the gravitational influence comes from matter we cannot directly see. Dark matter reveals itself through the shape of light. Imagine a distant galaxy glowing quietly across billions of light years. Between that galaxy and Earth is a huge cluster containing hundreds or even thousands of galaxies. The cluster itself is surrounded by an invisible concentration of mass. As the distant galaxy's light passes through the cluster's gravitational field, the path of that light is altered. To an observer on Earth, the distant galaxy may appear stretched into a curved arc, repeated in multiple places, or magnified into an unusual shape. The light has become a map of the invisible mass along its journey. The universe has left its fingerprints on the photons, and by studying those fingerprints, astronomers can reconstruct something that their telescopes cannot directly photograph. This is one reason dark matter is such a profound mystery. We have many independent observations suggesting that it exists, but knowing that something exists is not the same as knowing what it is. Scientists can measure its gravitational effects with increasing precision while still lacking a confirmed direct detection of the underlying particles. It is as though we can map the wind by watching leaves move, even though the wind itself remains invisible. The leaves are not the wind, but their motion tells us that something is passing through the trees. The possibility of invisible matter is not entirely surprising when we remember that the universe contains many things that do not emit visible light. Cold gas can be difficult to see. Black holes themselves do not emit light from inside their event horizons. Neutrinos interact so weakly that enormous numbers pass through Earth almost unnoticed. There are many forms of matter and radiation that are difficult to observe directly. But dark matter is different because the amount required to explain cosmic observations is enormous, and its behavior appears to be unlike ordinary matter. It is not simply a hidden collection of ordinary stars, planets, rocks, and clouds. The evidence points toward something fundamentally different. For a long time, astronomers considered whether dark matter might consist of ordinary matter that was simply difficult to see. Perhaps there were vast numbers of faint stars, planets, brown dwarfs, cold clouds, or other objects scattered through galaxies. These possibilities were investigated, and some forms of ordinary hidden matter certainly exist. But they cannot account for all the dark matter inferred from cosmological observations. The amount of unseen mass appears to be too large, and its behavior during the formation of cosmic structure points toward a non-luminous component that does not interact with ordinary matter in the usual ways. One of the most important clues comes from the early universe. The universe began in a hot, dense state and expanded and cooled over time. Tiny variations in density existed in the young cosmos. Over billions of years, gravity amplified these variations, drawing matter into denser regions and gradually building galaxies, galaxy groups, clusters, and the enormous filaments of the cosmic web. Dark matter appears to have played a crucial role in this process because it interacts gravitationally, but does not strongly interact with light. It could begin gathering into gravitational structures, while the ordinary matter was still coupled to radiation in the early universe. These invisible concentrations provided gravitational wells into which ordinary matter could later fall. Imagine the young universe as an almost uniform field with tiny differences that are difficult to picture. Some regions contain just slightly more matter than others. The differences are small, but gravity is patient. Over immense stretches of time, slightly denser regions pull in more material. As more matter gathers, their gravitational influence grows stronger. Filaments emerge. Dense knots become the homes of galaxy clusters. Smaller structures form within larger ones. The universe gradually develops the web-like pattern we see today. Beneath the luminous galaxies is a larger gravitational framework, much of which is made from matter that does not shine. The cosmic web is one of the most beautiful large-scale structures in nature. If you could somehow see the distribution of matter across an enormous region of the universe, it would not look like a random scattering of galaxies. Instead, galaxies tend to trace vast filaments and sheets surrounding enormous low-density voids. These structures can stretch for hundreds of millions of light years. At the intersections of filaments, matter becomes especially concentrated, forming galaxy clusters and superclusters. Between the filaments are immense regions with relatively little matter. Dark matter is thought to provide much of the underlying scaffolding of this structure. You can imagine the cosmic web as an immense, nearly invisible architecture. The galaxies are like small points of light placed along its threads. The threads themselves are mostly dark. Gravity has gathered matter into these structures over cosmic time, and the visible universe has formed within them. When we look at a deep field of galaxies, we see the luminous inhabitants of this structure, but we do not see the full framework directly. The darkness between the galaxies is therefore not simply an absence. It contains an invisible gravitational landscape. This landscape can influence the paths of galaxies for billions of years. A galaxy does not move through an empty stage without consequence. It travels through a gravitational environment shaped by dark matter, ordinary matter, neighboring galaxies, and larger structures. Its trajectory carries information about the mass surrounding it. Astronomers can use enormous surveys of galaxy positions and motions to reconstruct the large-scale distribution of matter. The resulting maps reveal a universe whose visible structure is closely connected to a much larger invisible component. The Milky Way itself is thought to be embedded within such a dark matter halo. The halo is not a sharply defined sphere with a physical surface. It is a diffuse gravitational structure extending far beyond the bright disk of stars. Its density gradually decreases with distance from the galactic center. The Sun moves through this environment as it follows its orbit around the center of the Milky Way. At this moment, dark matter may be passing through our region of space, including through Earth itself, without producing a noticeable sensation. If dark matter particles interact only extremely weakly with ordinary matter, billions of them could pass through us while leaving no obvious trace. That possibility has inspired some of the most sensitive experiments ever built. Deep underground laboratories have been designed to shield detectors from cosmic rays and other background signals. Researchers place carefully engineered materials beneath mountains or deep underground, hoping that a dark matter particle might occasionally interact with an atom inside the detector. The predicted interaction would be extraordinarily rare and subtle. A tiny amount of energy might be deposited in the material, producing a signal that could potentially be measured. The challenge is that ordinary radiation, environmental noise, radioactive materials, and even the materials of the detector itself can create signals that resemble what researchers are looking for. The quietness of these experiments is part of their beauty. Deep underground, far from the surface world, detectors wait. They do not chase dark matter. They simply remain ready. A particle may pass through the rock above, through the walls of the laboratory, through the detector, and continue onward without interacting at all. Every now and then, perhaps, something unusual may happen. Scientists record the event, examine its properties, compare it with known backgrounds, and ask whether it could have been caused by dark matter. Years can pass without a confirmed discovery. Patience becomes part of the experiment. Other searches look for dark matter in different ways. If dark matter particles can annihilate or decay under certain conditions, they might produce ordinary particles or radiation that telescopes could detect. Astronomers search for unusual gamma rays, cosmic rays, neutrinos, or other signals coming from regions where dark matter is expected to be concentrated. The center of the Milky Way is one such region. Dwarf galaxies, which can contain large amounts of dark matter relative to their visible stars, are another. The environments around galaxy clusters can also provide clues. These searches are challenging because astrophysical objects produce many natural signals, and distinguishing a dark matter signature from ordinary cosmic activity is extremely difficult. There are also experiments designed to create dark matter in the laboratory. Particle accelerators collide particles at extremely high energies, recreating conditions in which new particles might be produced. If a collision creates a stable, weakly interacting particle that escapes the detector without leaving a direct track, scientists may infer its presence through missing energy and momentum. This is a very different approach from underground detection. Instead of waiting for dark matter from the galaxy to arrive, researchers attempt to produce candidate particles themselves. So far, no confirmed dark matter particle has emerged from these efforts, but the searches continue. The lack of a confirmed particle is important. It means that dark matter remains a description of an observed gravitational phenomenon rather than a fully identified substance. We know what it does on large scales. We do not yet know exactly what it is on the microscopic scale. This distinction matters because science is not simply about finding names for mysteries. It is about building explanations that make accurate predictions. Dark matter is an extraordinarily successful framework for describing many observations, but the ultimate nature of the dark component remains an open question. There are many possible candidates. One broad class includes hypothetical particles that interact weakly with ordinary matter. Another possibility involves extremely light particles that could behave in unusual quantum ways across enormous distances. Some theories propose particles known as axions, originally introduced in a different context, but later considered as possible dark matter candidates. Other models involve heavier particles, hidden sectors, or particles that interact through forces not yet observed in ordinary matter. Each possibility has different consequences, and experiments are designed to test them. It is also possible that our understanding of gravity could require modification on certain scales. If the laws of gravity were different from our current theories, perhaps some of the observations attributed to dark matter could be explained without introducing a new substance. Modified gravity ideas have been explored for decades. Some can reproduce certain galaxy-scale observations remarkably well. But when we consider the full range of evidence, including galaxy clusters, gravitational lensing, the cosmic microwave background, and the large-scale formation of structure, dark matter remains the leading explanation in the standard cosmological model. Still, the possibility that our understanding could change is one reason the mystery remains scientifically alive. Science often advances through this tension between a successful model and unanswered questions. A theory can explain an enormous amount, while still leaving room for deeper understanding. Newton's laws described planetary motion beautifully, yet Einstein later showed that gravity could be understood more fundamentally through space-time geometry. Quantum mechanics transformed our understanding of matter while raising new questions about measurement and reality. Dark matter may eventually turn out to be a particle, a collection of particles, a new field, or part of a deeper theory of gravity and cosmology that we have not yet discovered. For now, perhaps the most useful way to think about dark matter is as invisible mass revealed through gravity. It is not darkness in the ordinary sense. It does not mean empty space. It means matter that appears not to interact with electromagnetic radiation strongly enough for us to see it directly. It can pass through light without shining. It can gather into halos. It can shape the formation of galaxies. It can bend light indirectly by curving space-time. And it can remain almost completely silent while influencing the largest structures in the universe. Consider the rotation of a spiral galaxy once more. Imagine traveling outward from the bright central region, past dense fields of stars, through the spiral arms, beyond the regions where most of the visible matter is concentrated. Eventually, the stars become sparse. If the galaxy contained only its visible material, the gravitational influence should weaken in a predictable way. Yet, the outer stars continue moving rapidly. The galaxy behaves as though an enormous invisible halo surrounds it. The stars are not falling apart into intergalactic space because the unseen mass provides additional gravitational binding. The galaxy is held together by something we cannot see. This pattern appears across many galaxies. Individual galaxies have different shapes, histories, environments, and distributions of stars. But the need for additional mass appears again and again. Some galaxies are dominated by dark matter much more strongly than others. Dwarf galaxies can be especially dark matter dominated. Their visible stars represent only a small portion of their total gravitational mass. In some cases, astronomers study the motions of just a handful of stars and infer the presence of a much larger invisible halo surrounding the system. Dwarf galaxies are therefore like quiet laboratories in the sky. They contain relatively few stars, making their visible structure simpler. But their gravitational behavior can reveal large amounts of unseen mass. Because they are often small and faint, they are difficult to discover and study. Yet, modern sky surveys have found many faint satellite galaxies around larger systems, such as the Milky Way. Each one adds another piece to the puzzle of how dark matter is distributed on small scales. The study of these small galaxies also raises important questions. Cosmological models involving cold dark matter predict that galaxies should form within many dark matter halos, including numerous small halos. Some of these halos may contain few stars or no stars at all, If so, the universe could be filled with invisible dark matter structures that have little or no ordinary matter inside them. There could be countless dark halos drifting through the cosmic web, influencing the motion of visible matter without containing enough stars to be noticed easily. Imagine a dark halo with no bright galaxy at its center. There may be no glowing disk, no spiral arms, and no visible stars announcing its presence. It could move through space almost unnoticed, revealing itself only through gravitational effects. Perhaps it passes near another structure and slightly alters the motion of nearby matter. Perhaps it bends the light of a distant object by a tiny amount. Perhaps it remains completely undetected. The universe may therefore contain a population of invisible structures that we are only beginning to understand. Dark matter also influences the shapes of galaxies. Computer simulations of cosmic structure formation show that when dark matter forms halos and filaments, ordinary matter falls into these gravitational wells. Gas can cool, condense, and form stars. Galaxies emerge within the larger dark matter architecture. When simulations include the right mixture of matter, radiation, dark matter, and dark energy, they can reproduce many features of the observed cosmic web. This is one of the strongest reasons dark matter is taken seriously. It is not simply a patch added to explain one strange observation. It is part of a broad framework that connects the early universe to the galaxies we see today. The cosmic microwave background provides another important piece. This faint radiation was released when the universe was young. Tiny fluctuations in its temperature correspond to variations in the density of the early cosmos. The pattern of those fluctuations has been measured with remarkable precision. When cosmologists compare the observed pattern with theoretical models, the amount of ordinary matter alone is not enough to reproduce the data. A substantial non-luminous matter component is required. The same general dark matter picture that helps explain galaxy rotation also helps explain the statistical pattern of the early universe. This is what makes the mystery so compelling. Dark matter appears at different scales and different times. We see its gravitational influence within galaxies. We infer its mass in clusters. We observe its role in gravitational lensing. We see its imprint in the cosmic microwave background. We observe the large-scale cosmic web that naturally emerges in models containing dark matter. These are independent lines of evidence, and together they create a remarkably consistent picture. Something invisible is present throughout the universe, shaping its evolution. One of the most striking demonstrations comes from collisions between galaxy clusters. Galaxy clusters contain three major components: galaxies, hot gas, and dark matter. The gas interacts strongly and can slow down during a collision, producing intense X-ray emission. The galaxies, because the space between individual stars is so enormous, can pass through the collision with relatively little direct interaction. Dark matter, if it interacts only weakly with itself and ordinary matter, should also pass through with little slowing. Gravitational lensing can then reveal where the total mass is located. In certain cluster collisions, the visible hot gas becomes separated from the regions where most of the inferred mass resides. The invisible component appears to have passed through more easily than the ordinary gas. These observations do not show dark matter as a glowing object. Instead, they create a map of where gravity says the mass is. It is an extraordinary situation. We can observe the ordinary matter directly through light and other radiation. We can map the invisible component through its gravitational influence. When the two maps separate, the distinction between visible and dark matter becomes difficult to ignore. Still, dark matter does not have to be imagined as a mysterious black cloud. It is probably not black in the same way that a shadow is black. A shadow is an absence of light caused by something blocking illumination. Dark matter is different. It appears not to emit, absorb, or scatter light in the ordinary way. A region filled with dark matter would not necessarily look dark because of the dark matter itself. Light could pass through it while being gently redirected by its gravity. The word dark is therefore a shorthand for invisible to electromagnetic observation. This is an important idea to keep in mind as the night grows quiet. When you imagine the universe filled with dark matter, do not picture a thick black fog. Instead, picture an invisible gravitational landscape. Imagine stars and galaxies moving through something that cannot be seen, their paths shaped by mass that leaves no ordinary glow. The darkness is not an object. It is the absence of direct light from the object. There is another reason dark matter is difficult to detect. Gravity is incredibly weak compared with the other fundamental interactions at the scale of individual particles. A dark matter particle could pass through an ordinary object without interacting at all. If it does interact, the event may transfer only a tiny amount of energy. Detectors therefore need to be extremely sensitive and carefully shielded. Researchers must distinguish possible signals from natural radioactivity, cosmic rays, thermal effects, electronic noise, and other sources. A confirmed discovery would require extraordinary evidence. This search has continued for decades. Different experiments test different particle masses and interaction strengths. Some use crystals, noble liquids, semiconductor materials, superconducting devices, or other technologies. Each experiment explores a different region of possible dark matter parameter space. The absence of a signal does not mean dark matter does not exist. It means that a particular class of models has become less likely. The search gradually narrows the possibilities. The same is true of astronomical observations. Telescopes measure the motions of stars, galaxies, and gas. Space missions map the cosmic microwave background. Large surveys measure the positions and shapes of millions or billions of galaxies. Gravitational lensing studies reconstruct mass distributions. Each measurement adds constraints. Slowly, the space of possible explanations becomes smaller. And yet, perhaps the most fascinating possibility is that dark matter may be more complicated than a single particle. Ordinary matter is not made of one kind of particle. It includes quarks, electrons, neutrinos, photons, and many other particles and fields. The dark sector, if it exists as a separate collection of particles and forces, might also have internal complexity. There could be dark particles that interact with one another through dark forces, perhaps forming structures or bound states that we cannot observe directly. Some speculative models imagine a hidden universe alongside the familiar one, connected to us mainly through gravity. These possibilities remain theoretical, but they remind us that the unknown may be richer than a single missing particle. Imagine such a hidden sector filling the universe. We would not see its stars because they would not necessarily emit ordinary light. We would not hear its signals. We might only notice its gravity. Perhaps dark matter could have its own interactions, its own history, and its own structures. Or perhaps it is much simpler, made from one stable particle left over from the early universe. We do not know. The universe has not yet given us enough information to choose among these possibilities. The early universe may hold the key. Many dark matter candidates could have been produced in the extremely hot conditions that existed shortly after the beginning of cosmic expansion. As the universe expanded and cooled, these particles could have become stable and survived to the present day. Their abundance today would depend on how they interacted in the early universe. In some theories, dark matter was once in thermal equilibrium with ordinary particles, and then gradually became rare as the universe cooled. In others, it could have been produced through entirely different mechanisms. The amount of dark matter we observe today, therefore, contains clues about the physics of the early cosmos. This is one reason cosmology and particle physics are deeply connected. The largest structures in the universe may depend on the properties of particles far too small to see directly. A galaxy, hundreds of thousands of light years across, can carry information about physics at microscopic scales. The motion of a star can tell us something about an invisible halo. The pattern of the cosmic microwave background can constrain the amount of matter in the universe. A detector deep underground can search for a single tiny interaction that could explain structures across billions of light years. The scale difference is astonishing. A particle smaller than an atom may influence the architecture of a galaxy. The invisible and the immense are connected. What happens at the smallest scales can shape what we see across the largest scales. The universe does not separate its mysteries into convenient categories. Particle physics, gravity, astronomy, and cosmology meet in the dark. Perhaps this is why dark matter is such a relaxing mystery to contemplate. It does not demand movement. It asks only that we imagine what might exist beyond the visible. The night sky becomes a doorway into a universe where most of the matter may be unseen. The stars are not the whole story. The galaxies are not the whole story. Even the beautiful cosmic web we can map through light may be only the luminous trace of a deeper gravitational structure. Let the image of the Milky Way return for a moment. The familiar stars glow softly in the darkness. The spiral arms contain enormous clouds of gas and dust. Somewhere among them is our solar system, moving through the galaxy. Around the visible disk extends a vast halo of dark matter. We cannot see its boundary. We cannot touch it. We cannot photograph it. But its gravity helps keep the galaxy together. The sun follows its orbit within this invisible environment, and Earth follows the sun. Every night, when we look upward, we see only a fraction of the structure that surrounds us. The dark matter halo is not perfectly smooth. Cosmological simulations suggest that it should contain smaller structures, streams, and subhalos. Some of these may have merged with the Milky Way over cosmic history. Others may still orbit within the halo. The galaxy has a memory written into the motions of its stars and satellites. By studying these motions, astronomers can reconstruct aspects of the Milky Way's past and infer the distribution of its invisible mass. The history of a galaxy is therefore not preserved only in its stars. It is also preserved in its gravitational structure. A satellite galaxy that was captured long ago may leave a stream of stars behind. A merger may distort the halo. Dark matter substructure may influence the distribution of stars and gas. The galaxy is like a vast archaeological site, but its artifacts are not stones or bones. They are motions, orbits, streams, and gravitational patterns. As you imagine drifting farther away from the Milky Way, the invisible halo becomes part of a larger halo surrounding the local group. The Milky Way and Andromeda are embedded within a shared gravitational environment. Beyond the local group are larger galaxy groups and clusters. Beyond, those are filaments stretching across the cosmic web. At every scale, invisible mass helps organize visible structures. The same basic force, gravity, operates across the hierarchy. And then there are the great voids. These enormous regions contain far fewer galaxies than the dense filaments surrounding them. They are not completely empty, but they are relatively sparse. Dark matter still exists within them, though at lower density, and the cosmic web gradually connects one structure to another. If you could travel through one of these voids, you might see almost nothing for immense distances. A few faint galaxies could appear far away. The darkness would seem nearly complete. Yet beneath that visual emptiness, gravity would still be shaping the motion of matter. This contrast between visible emptiness and invisible structure is one of the central themes of dark matter. Space can look empty while containing mass. A galaxy can look bright while most of its mass is dark. A cluster can contain luminous galaxies and glowing hot gas, while the majority of its gravitational mass remains unseen. The universe repeatedly reminds us that appearance and physical reality are not the same thing. Perhaps that lesson extends beyond astronomy. Human senses evolved to navigate a narrow range of reality. Our eyes detect a small portion of the electromagnetic spectrum. Our ears detect a limited range of sound frequencies. We cannot naturally sense magnetic fields, neutrinos, gravitational waves, or microscopic quantum states. Instruments extend our senses, revealing worlds that were always there. Dark matter may be another example of a reality that existed long before we developed the tools to infer it. The first astronomers who studied the heavens could not have imagined modern dark matter maps. They saw stars moving across the sky. They measured planets. They tracked comets. They developed calendars. Centuries later, telescopes revealed that the Milky Way contains countless stars. Then astronomers discovered other galaxies. Later still, they learned that the universe is expanding. Each step widened the known cosmos. Dark matter continues that tradition by telling us that even the visible universe is not the whole universe. The mystery may eventually become ordinary knowledge. If scientists identify the particle responsible for dark matter, future generations may learn its properties in textbooks the way we now learn about electrons and atoms. What seems mysterious today could become a familiar part of physics. But even then, new questions would likely appear. Where did the particle come from? Why does it have its particular mass? Why does it interact so weakly? Is there a dark sector? How does it connect to quantum gravity? Science rarely closes a door without revealing another hallway. For tonight, however, there is no need to walk through that hallway. Let the questions remain at a distance. Imagine the universe as a vast, dark ocean, but instead of water, let it be filled with invisible gravitational structure. Galaxies glow like distant islands. Filaments stretch between them. Voids open into immense, quiet spaces. Dark matter forms a framework that cannot be seen, but can be felt through gravity. Light travels through this landscape, sometimes bending around concentrations of mass, carrying ancient information from distant galaxies toward us. The path of light through the universe is especially beautiful to imagine. A photon leaves a distant galaxy and begins its journey. It may pass through regions where dark matter is concentrated. Its path curves slightly as space-time responds to the mass around it. The photon continues onward. Billions of years later, it reaches Earth. A telescope captures it. From that tiny arrival, astronomers can infer the presence of invisible matter along the path. The light becomes a messenger from both the visible and invisible universe. Gravitational lensing can reveal not only large dark matter structures, but also smaller ones. Tiny distortions in the light from background objects can reveal substructure within galaxy halos. This may eventually help distinguish different models of dark matter. Some theories predict that dark matter should form many small clumps. Others predict smoother distributions. By searching for subtle gravitational effects, astronomers can test how dark matter behaves on scales smaller than entire galaxies. This is an extraordinary example of indirect discovery. We may never photograph a dark matter particle. Instead, we could learn about it by observing how its collective gravity shapes the universe. The discovery process may resemble listening to a song through the vibrations of a distant wall. You do not see the source directly, but the pattern of the vibrations carries information. Future observatories will make these measurements increasingly precise. Large sky surveys will map the positions and shapes of enormous numbers of galaxies. Weak gravitational lensing will reveal subtle distortions caused by the matter between galaxies and Earth. By comparing the distribution of visible galaxies with the inferred distribution of total mass, astronomers can build increasingly detailed maps of the cosmic matter field. These maps may reveal how dark matter clusters, how it evolves, and whether its behavior matches the simplest models. Weak lensing is particularly interesting because it does not require a massive foreground cluster. Even small amounts of matter can produce tiny distortions in background galaxies. Across millions of galaxies, those distortions can be combined statistically. The result is a map of the large-scale gravitational field. It is like detecting a very faint pattern by listening to many quiet sounds at once. Individually, each distortion is almost invisible. Collectively, they reveal the structure of the universe. The universe, therefore, contains a kind of hidden topography. Mountains and valleys are not made of rock in this picture. They are concentrations and underdensities of mass. Galaxies occupy gravitational valleys. Voids are broad, low-density regions. Filaments connect denser structures. Dark matter helps define the terrain. Ordinary matter falls into this landscape and becomes luminous through the processes that create stars and galaxies. If you could somehow remove dark matter from the cosmic story, the universe would evolve very differently. The growth of structure would change. Galaxies might form differently or much later. The cosmic web would not look the same. The distribution of galaxies and clusters would change. The early universe would leave a different pattern in the cosmic microwave background. This is why dark matter is not a minor addition. It is woven into the history of the cosmos. Yet the word woven is fitting because dark matter itself may form an intricate structure. Simulations show halos containing smaller halos within them, streams left behind by mergers, and complex distributions shaped by gravitational interactions. A galaxy's dark matter halo is not simply a smooth, invisible sphere. It is a dynamic structure with a long history. It grows by absorbing smaller systems and by drawing material inward from the surrounding cosmic web. The Milky Way's halo may therefore contain remnants of galaxies that merged with it billions of years ago. Some of their dark matter became part of the larger halo, while their stars were scattered into streams and other structures. The galaxy we see today is a combination of many ancient histories. Dark matter may preserve some of those histories in a form that is invisible but gravitationally persistent. There is a quiet beauty in that persistence. A star can die, a galaxy can merge, and the light from an ancient event can continue traveling long after its source has changed. Dark matter can remain as part of the gravitational architecture. It is not a frozen substance, but it evolves slowly, responding to gravity over immense timescales. The universe remembers through motion. The longer we contemplate dark matter, the more the distinction between visible and invisible begins to feel less important. Stars are visible because they emit light. Dark matter is invisible because it apparently does not interact with light in the same way. Both contribute to gravity. Both can shape motion. Both are part of the same universe. One simply announces itself through photons, while the other speaks mainly through gravity. Imagine a galaxy cluster drifting through the dark. Hundreds of galaxies are scattered within it. Hot gas fills the space between them, glowing faintly in X-rays. Invisible dark matter surrounds and binds the system. The cluster moves through the expanding universe, its members orbiting within a shared gravitational field. Light from even more distant galaxies passes through the cluster and becomes distorted. Several different forms of information are present at once. Visible light from galaxies, high-energy radiation from hot gas, and gravitational distortions produced by unseen mass. The cluster becomes a natural laboratory for studying the hidden universe. The same is true of the cosmic microwave background. Ancient light travels across the universe and encounters structures along the way. Gravity from matter can subtly alter its path and temperature pattern. The background radiation therefore contains information not only about the early universe, but also about the matter it passed through. Cosmologists can use these effects to study how dark matter evolved over cosmic time. Dark matter is thus connected to both the beginning and the present. Its properties may have been established during the earliest moments of cosmic history, while its gravitational influence continues to shape galaxies today. A single mystery stretches across billions of years. The invisible component present in the young universe may still surround the Milky Way tonight. As you imagine the galaxy above you, remember that the stars are moving. The sun is moving. Earth is moving around the sun. The entire solar system is moving through the Milky Way. The Milky Way is moving within the local group. The local group is part of the larger cosmic web. All of these motions are governed by gravity, and gravity responds to both visible and invisible mass. The universe is not still. Even in the quietest night, everything is in motion. Dark matter does not need to push objects around like a visible force. Its presence changes the gravitational field, and objects follow the resulting trajectories. This is why astronomers can infer it from motion. A star does not need to know what dark matter is. It simply follows the gravitational environment around it. A galaxy does not need to understand its halo. It simply orbits within it. The universe does not label its components. We do that afterward, trying to describe what the observations are telling us. There is something peaceful about that. Nature does not rush to explain itself. The stars simply shine. Galaxies simply move. Light simply travels. Gravity simply acts. Human beings observe these patterns and gradually construct a story. Dark matter is one chapter in that story, a chapter written mostly in the language of motion rather than light. Perhaps someday we will know that our current picture is incomplete. Maybe dark matter is a new particle. Maybe it is an entire family of particles. Maybe gravity behaves differently under conditions we have not yet fully understood. Maybe dark matter has subtle interactions that will eventually become detectable. Maybe the answer will be stranger than any of these possibilities. Science leaves room for that uncertainty because the purpose is not to protect a favorite idea. The purpose is to follow evidence wherever it leads. For now, the evidence tells us that the universe contains far more gravitational mass than we can see in ordinary matter. That invisible component helped the cosmic web form, surrounds galaxies in enormous halos, shapes the motions of stars, bends light through gravitational lensing, and influences the evolution of the universe across billions of years. We may not yet know its microscopic identity, but its cosmic presence is difficult to ignore. And perhaps this is where the mystery becomes almost meditative. Look into the darkness and imagine that every visible galaxy is surrounded by something unseen. Not a monster, not a shadow, not a cloud, but a quiet gravitational presence. Imagine the Milky Way floating within its halo. Imagine the halos of neighboring galaxies overlapping through the larger local group. Imagine filaments of dark matter stretching across hundreds of millions of light years. Imagine immense voids between them. Imagine the entire visible universe suspended within an invisible architecture. You do not need to picture it perfectly. Let the image remain soft. A few blue galaxies here, a faint violet filament there, a warm golden star cluster far away. Between them, enormous spaces of deep navy darkness. The invisible structure is not something you need to see. It is enough to imagine that it is there. As the night becomes quieter, let the scale of the universe become slower. A galaxy rotates over hundreds of millions of years. A cluster moves across enormous distances. A cosmic filament evolves over billions of years. Dark matter halos grow gradually, merging and reshaping themselves. The universe has time. It does not need to complete its story tonight. You can rest while the galaxy continues to turn. The sun continues its orbit. The Milky Way continues through the local group. Dark matter continues to surround everything, quietly shaping the gravitational landscape. Distant galaxies continue shining. Ancient photons continue arriving. Some light bends around invisible mass and carries us information about things we cannot see. The universe is full of these indirect relationships. We know stars exist because they shine. We know planets exist because they move or transit across stars. We know black holes exist through their gravitational and energetic effects. We know dark matter exists through its influence on motion, structure, and light. Again and again, the universe teaches us that absence of direct visibility is not the same as absence of reality. Perhaps that is the deepest lesson of dark matter. The unseen can still be real. What we cannot perceive directly can still shape what we can perceive. The visible universe may be only the illuminated surface of a much deeper physical structure. The stars are beautiful, but they are not alone. The galaxies are magnificent, but they are embedded in something larger. The cosmic web glows with distant light, but beneath that light lies an invisible framework. Tonight, you can let that thought remain simple. There is more here than meets the eye. There is more mass than the stars reveal. There is more structure than the galaxies show. There is more history than the light immediately tells us. And there are still questions waiting beyond the edge of what we know. If dark matter turns out to be a particle, its particles may be passing through the space around you right now. They may be crossing the Earth without notice. They may have traveled through the galaxy for millions of years. They may have existed since the early universe. A tiny amount of their gravitational influence has helped shape the galaxies that now fill the sky. And yet, in your room tonight, you would feel nothing. The universe can be profoundly influential and almost completely silent. That silence is part of the mystery. Scientists build detectors deep underground and wait. Telescopes survey the sky and wait. Space missions collect faint signals and wait. The universe does not guarantee an answer. Discovery can take years, decades, or generations. But the search continues because the question is too important to ignore. Maybe the first convincing detection will come from a detector buried deep beneath the ground. Maybe it will come from an unexpected signal in a distant galaxy. Maybe a gravitational lensing survey will reveal a pattern that forces us to rethink our models. Maybe a particle accelerator will produce something that escapes the detector carrying missing energy. Maybe the discovery will come from an instrument that has not yet been designed. And when that day arrives, the universe will not change because we have discovered dark matter. The galaxies will continue to rotate. The stars will continue to shine. The invisible halos will continue to shape their motion. What changes is our understanding. A mystery that once appeared as a gravitational anomaly becomes a known part of nature. The darkness becomes a little more familiar. But even then, the universe will still contain other mysteries. Why is there more matter than antimatter? What is dark energy? How did the earliest structures form? What happens inside black holes? Is there a deeper theory connecting gravity and quantum mechanics? Are there other forms of matter or fields that we have not yet detected? The discovery of dark matter would not end the mystery of the universe. It would simply illuminate one more corner. For now, let that corner remain dark. Imagine a quiet galaxy floating through deep space. Around it is an enormous, invisible halo. Beyond it, other galaxies trace the cosmic web. Farther still are clusters and voids. Light travels between them, bending gently through the gravitational landscape. The universe expands. Time passes. The dark matter remains almost entirely unseen. You can let your thoughts drift with the galaxies. There is no need to hold onto any single image. Let the Milky Way fade into the distance. Let the spiral arms become soft blue ribbons. Let the stars become tiny points. Let the invisible halo become simply the idea of something surrounding the galaxy. Let the cosmic web stretch farther and farther until individual galaxies disappear. At that scale, the universe becomes almost abstract. There are no familiar landmarks, no roads, no borders, no walls, only structure, light, gravity, and immense time. Dark matter becomes part of the background, not because it is unimportant, but because it is everywhere. Perhaps that is why it is called dark, not because it is sinister, but because it does not speak through light. Its language is gravity. Its message is written in the rotation of galaxies, the motion of clusters, the bending of distant light, and the pattern of cosmic structure. It is a quiet language, but across billions of years, it has become loud enough for us to hear. And as you prepare to sleep, there is no need to understand that language. You can simply listen to the idea of it. Somewhere beyond the visible stars, unseen matter is moving through space. Somewhere inside a distant galaxy, stars are orbiting within an invisible halo. Somewhere in the vast cosmic web, dark matter filaments connect distant structures. Somewhere far away, light is bending around a concentration of mass and carrying an image toward us. The universe continues its quiet work. The night sky is therefore not a collection of lights suspended in emptiness. It is a living gravitational landscape. Every star has a history. Every galaxy has a halo. Every cluster has an invisible mass distribution. Every distant photon has traveled through a changing universe. And behind the visible structures is a deeper architecture that we are still learning to map. Let the thought become softer now. Dark matter does not need to be frightening. It is simply another reminder that reality is larger than perception. The darkness between the stars is not a blank canvas. It is filled with fields, particles, gravity, and structure. Some of those things shine, some do not. Together, they form the universe we inhabit. The Milky Way continues turning. Its stars continue along their enormous orbits. The sun continues its quiet path around the galactic center. Earth continues circling the sun. Above you, the night sky changes slowly as the planet rotates. Far beyond the atmosphere, dark matter continues to move through the galaxy. None of it needs your attention. You can rest while the universe continues. The invisible mass that helped shape the cosmic web is still there. The halos surrounding galaxies are still there. The distant clusters are still there. The great voids are still there. The ancient light is still traveling. The universe remains vast, mostly dark, and filled with things we understand only partially. And perhaps that is enough for tonight. You do not need to know what dark matter ultimately is. You only need to know that the universe contains more than the eye can see, and that the unseen can leave beautiful traces in the visible world. A galaxy's rotation, a curved path of light, a cluster held together, a filament across deep space, a tiny fluctuation in ancient radiation. These are the quiet footprints of something we cannot yet touch. So let your imagination drift once more through the darkness. See a distant spiral galaxy, glowing softly in blue and gold. Around it, imagine an immense invisible halo. Beyond it, other halos overlap and gather into filaments. Between the filaments lie enormous voids. Far away, galaxy clusters shine like faint islands. The whole structure extends beyond the limits of what any single telescope can map. There is no need to reach the end. There may not be an end. Let the cosmic web fade into the distance. Let the galaxies become smaller. Let the colors soften into deep navy and violet. Let the stars become gentle points of light. The unseen universe can remain unseen. Somewhere beneath the ground, detectors may be waiting. Somewhere in orbit, telescopes may be watching distant galaxies. Somewhere across the world, researchers may be analyzing measurements, looking for a tiny deviation that could reveal a new particle. Somewhere in the future, another observer may finally understand what we cannot yet explain. But tonight, you can simply sleep. The universe is patient. Dark matter is patient. Gravity is patient. The galaxies are patient. The questions will still be waiting when the morning comes. And as the final images of distant galaxies fade in your imagination, remember that the darkness is not empty. It contains structure. It contains history. It contains the invisible mass that helped shape the stars. It contains mysteries that have traveled with the universe since its earliest moments. You are resting inside that universe now, surrounded by ordinary matter that you can touch and invisible matter that you cannot see. The earth beneath you is part of a solar system. The solar system is part of a galaxy. The galaxy is embedded in a dark matter halo. The halo belongs to a larger cosmic structure, and that structure is one thread in a web stretching across the universe. Everything is connected by gravity, by time, by motion, and by the long journey of light. So let the universe continue without you for a while. Let the stars rotate. Let galaxies drift. Let dark matter pass silently through space. Let distant light cross billions of years. Let the cosmic web remain suspended in the darkness. There is nothing you need to solve. there is nothing you need to find. The mystery can remain a mystery. And somewhere in the vast quiet beyond the stars, invisible matter continues to shape the universe, almost completely unseen, almost completely silent, and yet written into everything we can observe. The galaxies keep turning. The stars keep shining. The light keeps traveling. The dark matter remains, and you can simply rest beneath it all.